This meeting is being recorded.
In this video from chapter 16, acid-base equilibria, we're going to take a look at acid-base behavior and how it relates to chemical structure. So there are a few factors that can affect our acid strength. So one factor can be the size of an atom. When we have a bond to a acidic proton, for example, if we look over here at our mini portion of the periodic table, as we get larger with HCl, so the HCl bond and then the HBr bond, as the atomic radius of our atom gets bigger and bigger, the proton becomes more and more acidic. So that's one factor that we can consider. Again, due to the length of the bond, the atomic orbital size. Then we have the number of oxygen atoms. So that's specific to this second type of acids called oxyacids. The first type we looked at were binary, where we always have this formula here, HCl, HBr, HI, H2O. They all fall into that category. And just like we can compare going down a group with atomic size, if all of our other atoms besides hydrogen are in the same period, if they're in the same row, we can compare electronegativity. So as they get closer to fluorine here, the most electronegative atom, we're going to see a weakening of those bonds. But this is really, methane here is really neither acidic nor basic. So that's one trend. The number of oxygens is another trend. And then always we have to consider the electronegativity of our central atom. So let's take a look at some other trends that we see down here. So as we mentioned, as the number of oxygens increases in a series of oxyacids, so we have hypochlorous here with 1 oxygen, we have chlorous with 2, chloric with 3, and then we have perchloric, right? We see 1, 2, 3, 4 oxygens here. So this is 2 of which of these are considered strong acids, and 2 of which are considered weak acids over here. So we can see this trend where they actually switch at this point from being weak acids to strong acids based solely on the number of oxygens. The reasoning behind this is that oxygen is itself a very electronegative atom, and it pulls away the electron density from the OH bond here, so that this proton is easier to remove as we increase the electronegative atoms in the acid that we're talking about here. So chlorous, right, 2 oxygens, even easier to remove that proton until we get to the strongest down here. Another factor that will definitely be mentioned if you have to take organic chemistry is resonance stabilization of conjugate bases. So what that means is after we pluck off a proton here, so there was a proton on this oxygen here, now it has this negative charge. What happens is these electrons kind of shift position, and then we end up with this resonance structure over here on the right. And this is actually a stabilization process. So when that is possible, when the conjugate base can do this resonance stabilization, that increases the acidity of a compound as well. So the acid, its pair, its conjugate acid, would be more acidic if the conjugate base can resonance stabilize. So we won't, that won't come up too much in this course, but definitely will come back, hopefully not to haunt you when you get to organic. So let's take a look at sample exercise 18 here, and we're asked to arrange these compounds according to increasing acid strength. So that means that we're going to put the weakest over here, and then our strongest over here. So I'll always check for any strong acid, so I see 1, so I'm going to put that over here. And then I notice that all of these heteroatoms, all these other atoms, these are in the same period. So I know that because I'm looking at a periodic table. The mini periodic table up here only has a limited amount of atoms, but the remainder of this row here, we have potassium, we have AS there as well. So in this row, all 4 of our other elements besides hydrogen are listed. So since these are all in same period, we're going to compare them by electronegativity. So we know bromine is the most, selenium is next in line. Then I have my ASH3 acid there, and then the weakest acid is this potassium. All right, so let's take a look at example B here and see if we can use similar rationalization. So these guys look pretty similar, except we have different numbers of oxygens, and then we have sulfur, and then we have selenium here as our central atom. So remember, always check for any strong acids in a question like this. So we're gonna put this guy, sulfuric acid, all the way over here, automatically as our strongest. And then we can check the number of oxygens, and since we have a different number of oxygens, we're going to put the one with the higher number here. So H2SeO4, and then our weakest acid in this series is going to be the H2SeO3.